the tricky part about reasoning is if you ask me a question that requires reasoning and I gave an answer to you, on the face of it, you can never tell whether I memorized the answer and gave it to you or I actually reasoned from first principles. My favorite example is in the old days when Microsoft started having these interviews, they apparently used to ask this question as to why are manhole covers round, right? And the very first sucker who had to answer this question basically had to do it from first principles. Basically, they had to realize that pretty much any other shape, you can manipulate it such that the cover falls through, and round is the only place where actually, if you can play with the covers and they fall through, then all these holes would be, coverless. And this is a neat way of thinking, but the first few people had to do this. Right now, when anybody asks this question in an interview, the only thing you will know based on the answer of the candidate is whether or not they prepared for the interview, prepared by looking up the web and looking at what are the usual Microsoft questions.
One of the ways to get better implicit reasoning with large language models when asking them questions similar to the manholes one is using the Brave Search API with retrieval augmented generation. It's an independent, affordable search solution that's making information retrieval way more efficient. Built from the ground up, Brave's index covers over 20 billion web pages, free from biases often associated with major tech companies. And what really sets it apart is its unique approach to data collection. Brave offers this powerful tool at developer-friendly prices, which scale with your business, making it an accessible option for projects of all sizes. So I encourage you to check out the benefits of the Brave Search API firsthand. You can start with 2,000 free queries monthly by visiting brave.com/API. Subbarao, it's an absolute honor to have you on MLST. I've been a huge fan from the sidelines for a long time now. Can you introduce yourself?
Yeah, so first of all, thank you for having me. So I am Subbarao Kambhampati. I've been an old professor at Arizona State University. I think this is my 33rd year. And I started working in AI as an undergrad. I was doing speech recognition like 40 years back, and then worked in planning and decision making most of my research career. Last 7 years or so, I was looking at explainable human AI interaction. And most recently, the last 2 years really, I've started looking at all these claims about the reasoning and planning capabilities of large language models. So that's sort of my journey.
Okay, so you've said that large language models are n-gram models on steroids, approximate retrieval systems or maybe even databases, and they can't reason or verify anything that they do out of the box.
Yeah.
Tell us more.
So first of all, I think the large language models, they are trained essentially in this autoregressive fashion to be able to complete the next word, guess the next word. And these are essentially n-gram models. They've been around since the time of Claude Shannon. The difference really is those n-gram models for n equal to 1 or 2 or 3. So we have pretty good understanding of bigram models, trigram models. If I say left and, you tend to think of right. And that's sort of the trigram model sort of a thing. What actually is happening here is that we really, even the lowly GPT 3.5 happens to be, sort of a 3,000 gram model. So that means given last 3,000 words, what's the most likely next word? It's the same idea except on huge steroids. And the tricky part about this is the number of 3,000 word sequences. If you have about a 50,000 word vocabulary, is 50,000 power 3,000. And so if you are trying to keep occurrence statistics, which is the normal way to do n-gram models, we run into two problems. One, of course, is this a humongous, set of rows for which you need to have, conditional probability table and what's the next word that's likely to come. And secondly, the other problem is the possibility that the same 3,000 words will occur more than once is essentially zero. And 3,000 is GPT 3.5. Right now, we are talking about million word models. So the thing that's surprising about LLMs basically is we essentially have are able to train this really large base, and there's huge amount of compression that goes on. So I tell students that, when you think of GPT 3.5, right, people will be surprised that it has 176 billion parameters. And I think, no, you should actually be so happy that it's only 176 billion, because if you really are trying to do it in the full first principles way, you would wind up having 50,000 power 3000. That's actually infinity, in some sense. So because there's this huge compression going on, interestingly, any compression corresponds to some generalization, because you compress, so some number of rows for which there would be zeros before, now they might be non-zeros, and so for some words. And so this, what we found empirically is that when you complete with these trained models, they are giving completions that have very interesting properties. In particular, it's a generative, it's a sort of a generative AI system. And so they capture distribution extremely well. And what that means is they capture the style of the data on which they have been trained on. And as English as a second language speaker, I learned English with grammar rules, which kind of almost makes no sense. But that's, your first language, you don't learn grammar, you just learn to speak language. Second language, you tend to follow some rules and exceptions and rules and exceptions. And that's a kind of pretty hard way to learn a language. And I was continually impressed when GPT-3 and GPT 3.5 came around that they can't make a grammatically incorrect sentence. You almost have to prompt them to say, imagine you are an Indian grad student just arriving or something, and then they will make a thing. So the point is, grammar essentially is a sort of a distributional characteristic, and they capture that. And it's a very impressive thing. And, people got very surprised that this is happening. And then so they, for any arbitrary prompt, they're able to give very plausible, very good English completions. Because we just completely didn't expect this at all, when our intuitions go, haywire, we tend to think that everything is now possible. So surprisingly for humans, actually, in fact, when I was speaking English as a second language, I knew what I wanted to say. I knew the content of what I wanted to say. It was the damn language, putting it in the right grammar, that was getting in the way, right? And so I would tend to assume that if something can actually speak the language, maybe the content is easy, because content was always natural to me. That is where people start thinking LLMs, because they can speak, write good, high, grammatically correct English, the good form language of any kind, programming languages, English, etc., etc. Maybe they have already got the content fine too, because we actually find content easier and the style harder. Okay, and that's actually the place from which all these reasoning claims for LLMs and the factuality claims for LLMs come, and it just, they don't hold for n-gram models.
This might be an interesting digression, actually, but there is some debate whether natural language is a formal language.
It never was. I think, from the way I understand it, in essence, one interesting way of thinking about it is, like, for example, programming languages are formal languages. For formal languages, you can have interpreters, which are actually one of the things that people get confused is, like, basically for when these kinds of LLMs guess code, okay, there is a way of checking what that code would produce, because there is a Python interpreter that can take anything that is grammatically correct Python and tell you what would come as output. There is no such thing for natural language, because natural language essentially captures everything. It's not just Python. It's actually about all possible scenarios in the world, and world is the interpreter for natural language. Whereas, and so because of which you actually, it's a much more flexible, much more unconstrained form of expression, the sub parts. If you go from like programming languages to even something as simple as first order logic, which is a formal language, you already see that by that time, interpreters become hugely unwieldy. They're extremely costly to, computationally costly to interpret even first order language. And we already know that first order language is not expressive enough. Okay. So that is a great thing, because in many ways I tend to think that a formal language, oftentimes most reasonable formal languages tend to have interpreters. For natural language, the world is the interpreter. and so that's a way of seeing. And that's actually the appeal of natural language, because you can pretty much say almost anything. I understand that there is this tacit versus explicit difference, but in general, pretty much you can express the expressiveness limitations of natural language are so much smaller compared to pretty much any formal languages. And that's where the interpreters are actually possible to get for those.
Yes, and we will get to the verification gap in a minute, because wouldn't it be great if we could build a verified language?
Yeah, indeed, yeah.
But sticking with the reasoning thing just for a minute. So people out there are convinced that language models reason. I mean, for example, I had Raphael Millier on the show, and he was citing the example of Othello. And there was that paper where it's a board game, kind of similar to Go, and they said that it was learning this abstract world model, and it was generalizing. Why do people believe so deeply that these things reason?
So that's a very interesting question. The tricky part about reasoning is, if you ask me a question that requires reasoning and I gave an answer to you, on the face of it, you can never tell whether I memorized the answer and gave it to you or I actually reasoned from first principles. My favorite example is in the old days when Microsoft started having these interviews, they apparently used to ask this question as to why are manhole covers round, right? And the very first sucker who had to answer this question basically had to do it from first principles. Basically, they had to realize that pretty much any other shape, you can manipulate it such that the cover falls through, and round is the only place where actually, if you can play with the covers and they fall through, then all these holes would be, coverless. And this is a neat way of thinking, but the first few people had to do this. Right now, when anybody asks this question in an interview, the only thing you will know based on the answer of the candidate is whether or not they prepared for the interview, prepared by looking up the web and looking at what are the usual Microsoft questions. And of course, humans being humans, they will also try to say, even that people want to know whether you can reason. And so if you actually happen to know the answer, if you blurt it out, that would give it away. So you would take some time and then blurt out the answer. And so you can't tell just by the end part whether I was reasoning or retrieving. And in general, this is true. And the one reason why we think humans cannot just get by with full-on retrieval is we have a life. We basically tend, even the craziest interview preparing people will basically spend a bunch of time looking up the old questions, but then they still depend on being able to do some first principles reasoning if the question is not anywhere in the question bank, right? That's not a problem for LLMs. So to some extent, like for example, many of these reasoning claims come from facts like LLMs are extremely good on the standardized tests, right? And the thing that people forget about standardized tests is standardized tests have standardized question banks. And I keep telling my students that the hardest people, you think that the hard part is answering the exam questions. Really, the hard part is coming up with interesting exam questions that haven't already been listed on the course hero, which is like this website of the kinds of the websites that exist now, where they take every possible question that has ever been asked on the exam or put on a question bank with the answer. And so students can pretty much try to prepare to the test rather than prepare to understand the material and then answer the questions on time. So this ultimately winds up being, in many cases where people think LLMs are reasoning, it winds up being the case that they're actually doing approximate retrieval. Now, how do you show that? The usual way you get to show that is by a diagonalization argument. You almost, for example, I'll give you an example. So I am interested in planning capabilities of large language models. Planning is a form of reasoning. It's a form of reasoning involving time and action. So one very simple kind of planning problems that people in AI planning have been looking at are things like block stacking. That is, you have a bunch of blocks in some configuration in the initial state. They could be just named blocks or colored blocks. And you want to have a different configuration in the goal state. And there's a bunch of actions such as picking up, putting down, stack, unstack, right? Given these actions, given this blocks world problem, can you come up with a sequence of actions that actually will lead to the goal state? That's the planning problem. Interestingly enough, original LLMs like GPT-3, etc., were very bad at this. GPT 3.5, in fact, and GPT-3, in fact, I think in 2022, we wrote this thing when everybody is making claims about planning capabilities that no, they can't. In fact, they get close to 0.6% accuracy. They're just guessing, and then the action sequence won't lead them to goal. Interestingly, when GPT-4 came, and you might remember that Sebastian Bubeck and co wrote this, the notorious Sparks paper. And so we were interested in seeing maybe are there the Sparks going to help the planning capability? So we checked GPT-4. Interestingly, it increased in accuracy. It's still nowhere near 100%, but it went from something like 0.6% to close to 30%. So you can argue that, wow, if GPT-4 is 30%, GPT-5 would be maybe 70%, and by GPT-10, you can get 150% accuracy of some sort, right? The question that we asked ourselves is, can you explain this potentially in terms of just the retrieval as against actually reasoning? If you are doing reasoning, then if I take the blocks world and change the names, things like instead of stack, I will say feast. Instead of unstack, I will say slap, something like that. So if you have any background in logic, you realize that the predicate names don't change the dynamics of the system. And so any planner which can solve the original domain can solve this with exactly the same efficiency and accuracy. You give this to GPT-4, it dies. And in fact, we wrote this paper called Plan Bench paper for NeurIPS 2023, which essentially shows both the blocks world logistics kinds of planning problems as well as these obfuscated versions of them. And it's almost like a fun sideline for us that Karthik Valmikam, who is the lead author on that paper, he keeps running every new sort of LLM, GPT-4o, and Claude, and Gemini, and they all basically are stuck close to zero because they are essentially guessing the plans for blocks world because they have the word, they have the usual words associated with blocks world, which are stacking, unstacking, etc. And there's enough of the data for that in the web scale corpora. But you change the words, they're completely lost. So that is a great way of showing essentially that they are not doing reasoning. Because if you were doing reasoning, you should be able to solve this just as easily as the original one. So in general, I can understand why people easily fall for this because typically, as I said, when people answer a question that requires reasoning, you can't tell just on the face of it whether they just happen to have heard the question and the answer before they came into the room and they just blurted it out, or did they actually start from that question and answer it by reasoning for
It might be interesting to have a small digression on what reasoning is. Now, I'll give you my definition. So I think it is performing an effective computation to derive knowledge or achieve a goal using a world model and all existing semantics. So, you can think of it very loosely as, deriving kind of truths that we don't currently know, if that makes sense.
Yeah, so I would go back to, first of all, reasoning is pretty well defined from a logical perspective. That's one particular kind of reasoning that we have understood from the Greeks on, right? And that I always find that it's useful to just go back to that, even though there's all sorts of reasoning. Logical reasoning is certainly one very important kind of reasoning. And as you said, in the case of logic, given a set of base facts, you're trying to see whether some new facts will follow, in the sense is the deductive closure of the knowledge that you have, are these other things present. So this is actually a very important distinction. So everybody in AI used to know logical background, but nowadays most of the grad students actually start with just deep learning courses and machine learning courses. This is very important technology. I'm not questioning that at all, but you need to understand that the in versus out of distribution, the usual terminology that people use in machine learning, that's for databases. For reasoning, you need to think in terms of deductive databases at the minimum, which is you're not just looking to see whether the stuff in the database, basically whether the query that you're asking is in the same distribution as the kind of queries that you already presented previously. Instead, you're looking to see whether the system is able to compute things in the deductive closure. Okay, that's what winds up requiring logical reasoning, and there's no reason to believe that LLMs can do that. And one of the very interesting, first of all, there's actually increasingly more and more evidence showing that this definitely can't do it. We've been saying that as a corollary of the fact that they can't do planning, they clearly must be failing in doing, deductive closure. But people have even shown, recently there was a paper which talks about a sort of a transitive closure. Transitive closure is a poor cousin of deductive closure, which is if you, let's say, A, P1, B, P2, C, okay, you should be able to say A, P1, P2, C, right? They can't even do that. And if you have to actually train them, in addition to their normal base facts, you have to give them additional facts from the deductive closure, and then they might try to do a little bit more generalization there. But then even after that, they would not be able to do A, P1, P2, P3, D, because that's again an extra step, and they just don't realize that there is a method to this madness, that you're essentially looking at transitive closure. If A is connected to B and B is connected to C, C is connected to D, then A is essentially connected to D in this P1, P2, P3 way. If you can't do that, you certainly can't do deductive closure, because transitive closure is a really small part of deductive closure. And so that's one way of realizing that LLMs cannot do reasoning. Now, people say, but no, there are things that LLMs are doing that are not considered base facts. But that actually is because we don't really understand the training data. The training data is not something that we put together. It is the entire web. And everybody thinks that they know what's on the web. Nobody really understands how many things are on the web. So I keep remembering this thing that when Palm, the old Google LLM, came about, one of its great claims to fame is it could explain jokes. Why is that like an AI task is beyond me. But it is surprising that it could kind of explain jokes. And so you'll be very surprised, wow, it is actually able to do some sort of thing that's beyond the data. But really, I don't know whether you know this, but there are humor challenged people in the world, and there are websites that explain jokes. And these websites are part of the entire web crawl that the system has been trained on, and because of which it's not that surprising. So reality is, in normal logical terms, you would think that I gave base facts and the system says something that's not typically a base fact, then it must have done some kind of a reasoning. But oftentimes the web corpora contain both what we would consider base facts and what we would consider parts of the deductive closure in an interesting mishmash way. And so when once in a while it actually winds up retrieving the stuff from the deductive closure, you would think it's actually reasoning, because you think it couldn't have probably been in the web. That's because you don't know actually what's on the web. It's like, it's very hard to show that what is and what is not on the web. I actually have an experiment that this Tom Griffith's group did that I really repeat to a lot of people. That again makes the same kind of a point, which is one of the sparks that the original GPT-4 paper talks about is that GPT-4 can do ciphertext decoding, right? And Caesar cipher decoding. And so what these guys basically did is check, because Caesar cipher decoding is just basically based on like an offset, right? And so you take A plus 4, then you take the 4 letters off from A and then replace A by that. That's the usual thing. So for each offset, there's a code. And so they try to see how well does the system, GPT-4, decode for different offsets, 1, 2, 3, 4, all the way to 25. And surprisingly, they find there's a huge peak at 13, and it's basically close to 0 anywhere else. And why is that interesting? If you remember, or if you're old enough, you'll remember that in Unix, there is still a command called rot13. Rotate by 13, which is, while Caesar cipher is a general idea, 13 is the special case, that is rotating letters by 13 is the special case that Caesar cipher is more famous for. And there's tons and tons of data of normal text and rotated by 13 text on the web. So that's the part that LLM does well, and it doesn't do well for 2, 3, 4, all the way, and any other number. A little kid who you explain to them what the point of Caesar cipher is will now have no trouble doing either 13 or 4 or 2. In fact, they might find it easier to do 4 because it's easier to count to 4 than to count up to 13 and shift the letter. And yet, it's one of these cases where you would be surprised at what is called emergent reasoning capabilities. And I think if I might be so bold as to say what's somewhat wrong about the kind of empirical studies on LLMs is that people tend to stop at the first sign where they get interesting results. And I think you have to be very skeptical. You have to assume by thinking that the system does not have, certain capabilities, and then actually try to, poke holes rather than write a paper right away. And currently we are going through a hype cycle where essentially both in research and in commercial terms, where people are just happy to write LLMs are zero-shot XXX, where XXX is reasoning, planning, something else, and mental modeling, etc., etc. And it turns out for most of these, you can find that really you can explain the results from an approximate retrieval point of view, because by diagonalizing, in fact, as I mentioned, the planning where you change the names, that's a diagonalization argument. What these guys did in checking whether it can do ciphertext decoding for something other than 13 is another diagonalization argument. Because if you know the general principle, you should be able to do it. If on the other hand, you're memorizing, you won't be able to do it. And so that's a classical way of finding, but showing that it's not doing reasoning. But I agree that typically, in general, it's easier to be impressed because coming up with these diagonalization arguments is hard. But from a scientific perspective, we need to see, whether or not they actually have these capabilities.
Yeah, a few thoughts on that. It's interesting that people are not more skeptical. My religion is skepticism.
Yeah, I think so. Science is supposed to be skeptical in general. And I think I find this fascinating. It's like, in addition to the research implications, it also kind of says a lot about the sociology of research. Yeah. And in general, humans are not good at giving credit to anything. In general, they would like to say it is their idea, except strangely enough, with LLMs, they are willing to give credit to LLM than to themselves, because I think my cynical way of looking at it is, if you say LLM did it, you get a New Rips paper. If you say you did it, who cares? It's not supposed to be impressive. But to some extent, people are suspending their disbelief too easily. And that is not a good thing for science. If you're doing it, if I'm a startup, clearly, the whole point is let's hope that the world suspends their disbelief while I make my millions, right? But science, it's a different thing. And so one of the interesting questions is what's going to be the half-life period of many of these LLMs or zero-shot XXX kind of papers. I have this full-on tongue-in-cheek. I have said on Twitter that when some of these papers are shown to be kind of wrong, they should lose their citations. Right now, what happens is the bad papers, which actually made claims that actually were proven to be wrong, they still keep gaining citations because people will say, they said this and it was wrong. I think one way of designing the mechanism is that if I prove your idea to be wrong, I should get all your citations for the bad. Because that's to the extent for us, the citations is the currency. I mean, obviously I'm being facetious, but in general, that reduces the incentive for people to rush to print and hope that maybe, basically they may be right. And even if it's not right, they will get some amount of attention. This is exactly what you have to do as a startup. Because you want, there's the whole first rule there's this 21 rules of marketing, that thin book. And it says the first rule of marketing is it's better to be first than to be better. Right. Yeah. But research is supposed to be different, right? And so we have become a lot more like it's better to claim something as the first person and then get it into NeurIPS or iClair and wait for other people to figure out whether the claim is right or wrong, than to do your own due diligence beforehand. And that is playing out right now in a larger sense. It's like this is more of the sociology of science. It's a human endeavor after all. Most of research is human endeavor. So these motivations matter.
Yeah, so science should be like that snake game where, when you kill another snake, your snake grows by the size of the snake that you just killed.
It should be. Yeah, exactly.
Yeah, but a couple of things on that. And first of all, actually, when I speak with, X-risk people, they also make a slightly hedging argument where they say, similar with your marketing argument that, it's better to be there first. Mm-hmm. They say, well, it's better to have like a big, inefficient, dumb AI because you can just approximate a smart AI with a dumb AI. And that's kind of what language models are doing because they're doing this mechanical Turk thing where wherever it's doing bad, we'll just throw more data or do augmented data. And then it creates this kind of illusion where people anthropomorphize it. And it seems to do well because it's been trained in many, many specialized situations to do the thing. But I wanted to quickly come back to reasoning because what you were saying was brilliant. I'm a big fan of Walid Subbarao. I don't know if you know him, but he's talking about transitivity and deductive closure and all this kind of thing. And I want to bring in creativity. So first of all, when we do deduction, we are applying these rules that could work in any situation. But if you think about it, we can compose these deductive rules into this big kind of tree, into a big graph. Mm-hmm. It's similar to in the physics world. We talk of the physics world being causally closed, but we're talking about like a deductive closure. And what is the role of creativity when we traverse this graph?
That's it. First of all, that's an excellent question. In general, this actually, so despite what the tenor of our conversation until now, I actually think LLMs are brilliant. It's just they're brilliant for what they can do. And I don't complain that they can't do reason, use them for what they are good at, which is unconstrained idea generation. Okay. And in pretty much every human field, even fields of endeavor, you have this interesting juxtaposition between the creative idea generation and the laborious deductive idea shaking. Okay, even in math, this is true. Fermat came up with this conjecture and of course also claimed that he proved it. And Andrew Weil spent 17 years of his life 200 years later to actually prove that what Fermat was saying is actually, provable with respect to the mathematical axioms, with some math that was invented much later than Fermat, right? Fermat. And same with everything. So, there's this beautiful book that I keep telling people about Gregory Perelman's, life story called Perfect Rigor. Gregory Perelman, as you might remember, basically proved the Poincaré conjecture, and he refused, taking the Fields Medal because saying I did it for the mathematics of it, not for external validation. But the more interesting part is the way he wound up actually completing the proof involved using somebody else, I forget this mathematician in Berkeley, who actually made a conjecture, a creative conjecture about combining two very different fields of mathematics and saying, if this holds, then this will actually work. And then actually, Perelman went on doing this laborious backbreaking work of actually showing that it does hold. Okay, creativity, math requires both the creativity as well as deductive thing. And sometimes the same mathematician has both of them. Sometimes it's also the case that some mathematicians are better at the actual proof part and some are better at seeing the creative connection. Ramanujan, the guy from India, is like the most famous of his lot because he seemed to have had a creative generator that almost had a much higher density of being correct. And so he would just write these huge, crazy series and write the answer with no proof. And, G.H. Hardy basically famously said, they must be true because if they weren't, nobody would have the imagination to write this. He was obviously being facetious. I mean, he was just a great, supporter of Ramanujan's work. But in general, the creativity part is something that LLMs are extremely good at. And in any kind of a theorem proving sorts of things, you can do shortcuts by coming up with interesting hypotheses and proving that, because there's just too many. It's just, if you try to do it in the first principles way of looking at all possible theorem proving paths, it's essentially impossible. I mean, this corresponds to, there is bigger reasons too. There's a Gödel incompleteness theorem. If you remember, Hilbert was trying to basically automate mathematics by saying, it's all nothing but logical theorem proving. And Gödel said, even that's not true. But even if it were true, even if it were the part of math where it's really just showing deductive closure, computation of deductive closure for a large enough system is like horrendously inefficient. And so you need to make inductive leaps. There's nothing wrong with having ideas. The only thing that civilization needs is that when you get the idea, you check whether the idea works. That's the robustness aspect. If it doesn't work, you give up on this idea, go for something else. And we typically find that verification of an idea is easier, having the idea is harder. In fact, in our lifetime, in our lives, we would have friends sometimes who are fount of ideas. So you get stuck, you ask, hey Tom, do you have an idea on how to do this? Tom may not have a big stake in this, but they are good at generating ideas. They'll give an idea, and it's your responsibility to check if it actually works. And when it does work, we tend to give much more credit to Tom because Tom gave the idea. But Tom didn't prove that the idea was right. Okay, you proved it. And it's easy for us to kind of verify, and we think idea generation is the more important thing. LLMs are actually good for the idea generation, and they're actually bad for the thing that is easy for us to some extent, which is verification. And so in general, that sort of the creativity part is making the inductive leaps to cut down the search, so that if you just make an idea and you don't actually check if it works, then it's just an idea. Okay. But then once you can, if you have hopefully a generator of ideas that has a higher density of good ideas, it can reduce the search quite significantly in terms of, and so that's sort of the way creativity and the reasoning come together. So inductive versus deductive leaps, right? An inductive leap versus deductive closure, okay? The inductive leaps basically are all the imagination, all the creativity part, and LLMs are actually quite good at some of those things because it's no skin off their nose. They're giving you ideas. You ask and they will give you ideas. But you have to check whether that idea actually makes sense in the context of all the constraints of the problem. And in general, people in like more creative fields, like things like design and like engineering design, which straddle the creativity aspect as well as the realizability aspect. Architecture is another one. They tend to almost say that during the ideation phase, you need to be unconstrained. And then once you get good ideas, then you have to make sure that actually the building which looks like that can be supported with the kind of strengths of materials that we currently have. Otherwise, it's just a beautiful looking building that you cannot build it. And so this second part is equally important. And, one of the hope is when people, do architecture courses, let's say, they tend to constrain their generator, their ideation phase, such that they're more likely to come up with ideas which are likely to be realizable. So this is a slow thing, but that's my way of looking at where the creativity and the reasoning part come in, and it's very relevant with LLMs, because I would use LLMs for their creative things, mostly because ideas require knowledge. It's like ideation requires shallow knowledge of very wide scope. And most of us don't have, like, for example, you want to give some idea about, this is another place. Analogies are a great case where LLMs actually do better than normal, people, a man on the street. And to do analogy, you need to have at least a significant amount of knowledge about the world. So if you want to sort of analogize how things in Finland will work, knowing how things in India will work, you need to know something about these countries. And not everybody might know them, so they may not be able to construct those analogies. Whereas LLMs actually have been trained on the entire world's data, and so they can make these kinds of shallow, unguaranteed leaps. And then you have to pick up and check whether or not that thing holds. So that's one great place for them.
Yeah, I mean, let's just explore this a tiny bit more. I mean, I agree there is a beautiful symbiosis between the generation of ideas and the verification of them. But and also you've said that even though we can be pessimistic about LLMs, in many ways, actually, they are incredibly useful. But if you don't mind, I want to just gently push on this creativity thing. So you said that, what was the term you used? Yeah, that's... In order to generate ideas, we need knowledge. But reasoning is about creating new knowledge. And if you think about it, we could just be completely open-ended when we generate our ideas, and that wouldn't be very good. Or it can be guided by intuition or existing knowledge. But I think there's a difference between inventive creativity and combinatorial creativity. So I think there should be some form of reasoning even in the creativity itself. And that leads me to think that language models are surely limited in the types of things that they can create, because they're bounded by the training data.
I agree, but my point is that compared to you and me, they have been trained on a lot more data, that even if they're doing shallow, almost pattern match across their vast knowledge, to you, it looks very impressive and it's a very useful ability. So there is this entire question as to, actually there's this very interesting point about whether in fact the creativity that a machine creates is considered, as you said, combinatorial versus something beyond. But that becomes almost a second order question if you don't even have, a tool which actually generates this combinatorial creativity over vast knowledge. And, in that sense, again, I am actually not viewing LLMs in terms of AGI connections as much as incredibly useful tool. And for computer-supported cooperative work in particular, where it's cooperative with the humans or cooperative with other reasoning systems, that makes a lot more sense. That's where they really shine. And for that perspective, I am willing to use them for that creativity aspect. I would almost never use them for reasoning aspect, because reasoning requires some kind of a guarantee that what you said is actually true. And I can't believe that they are not going to be able to do that for at least the usual correctness considerations. They can do it better for style in general. That means they can create an essay that looks more like a well-written English essay, as against making sure that the content of that essay is actually factual, and that there is, and maybe even making interesting deductive closure claims, which is actually going from the premises towards, more interesting. That's the part that I don't believe LLMs can do, but they can write and also check the style of another essay, because that's what they're good at. And to some extent, actually, this is autoregressive LLMs are a specific form of generative AI. And generative AI learns properties of a distribution. Style is a distributional property. Correctness and factuality is a instance level property. And LLMs do very well on the distributional properties because they're distribution learners, and they are not going to give you any guarantees about instance level correctness. And so that we do have other tools for, obviously, and we can put them together.
Yeah, interesting. So it sounds like we're saying there is a verification and reasoning gap and potentially a creativity gap, but the reasoning gap is much bigger.
Much
so
bigger.
We should focus on that. But the other thing, of course, is that because we're talking about building this mimetic system where humans are engaged, so we're always doing creative things. We produce data. The data goes into the language model. So we're creating this big collective intelligence.
Exactly.
And in a sense, let's say you do something creative tomorrow, it will be in GPT-4.
Yeah, exactly.
Yeah. So the whole thing just...
It is. That's the way to think about it, because in essence, they are tools, and we build them tools to some extent. I keep actually telling people, many people don't realize, as you very well put just now, that they are scaffolded over our collective knowledge. So I keep asking people to do this thought experiment. Imagine Sam Altman got Satya Nadella to already pay for training GPT-K, right? And he just didn't have web, right? And he had to create the web. And so he comes and says, guys, why don't you just put everything you ever wanted to talk about on the web so that I can use this as a data? That would be dead on arrival, because nobody would do that. We made web for each other's to actually, kind of communicate with each other. And that then became fodder for these systems. So in a way, the fact that these things are doing well is very much based on the fact that they are doing shallow pattern matching-ish sorts of things over this vast knowledge that we have put on the web. It'll be a lot more impressive if in fact somehow it was a Martian who basically had no access to any of what we created, and yet they were able to help us. That's AGI kind of thing. But I'm very happy with tools. I'm very, very happy with tools that I think Google is a great tool, right? And would you say Google is like AGI? It doesn't matter to me. It's extremely useful because it was telling me, information that other people know that I don't know. And so that basically is a very reasonable way of looking at these amplifying, effects of these kinds of technologies. And, but it's very important to remember that they're not creating this. In fact, if you make them create knowledge, create kind of text, and my biggest worry is, I actually said this, that, in Norway, there is this seed vault. And they basically have a vault in somewhere high up in northern Norway, where they kept all the seeds of the things, just in case there's some nuclear this thing, etc. And we need to restart the civilization. You have seeds there. Yeah. And I always felt that we need to take a snapshot of our current web and put it in that seed vault, because as LLMs generate more and more completions and they become part of the web, essentially, you are now have a much more noisier version than things like Wikipedia and New York Times, etc., which are a lot more curated kinds of sources. And when it's all combined, it becomes much harder to tell, which is which already. And so that sort of tells you how important it was that the data that they've been trained on was not actually generated by them at all. And And so when people talk about you can somehow, you don't need human data. I mean, not too many smart people say that, but a few, not well-informed people think that somehow, why can't LLMs just create data and train themselves? That's essentially blind leading the blind. And it's actually becomes much worse because, the completions are only the distribution. They're not really have any kind of an accuracy. And so the factuality goes even more down. And when people talk about synthetic data, typically what they'll wind up doing is they'll depend on some external solver which actually produces the synthetic data with guarantees. So if I want to kind of do better planning, I will create a huge number of planning problems, use an existing outside planner to solve them, and then now have the problem and the plan. I fine-tune my LLM so that it sort of becomes slightly better at generating solutions for this distribution of planning problems. If it just generates plans itself and trains itself, that would be, blind leading the blind.
Yeah, just a quick digression on this. Are you familiar with Chollet's ARC challenge?
Yes.
Because that's a great example. So, I mean, I'm friends with Jack Cole and the winning team, and they've done data set generation and test time inference and fine tuning and so on, and they've made a whole bunch of transform rules, so the reflections and symmetries and stuff like that. And they're kind of like building up the data distribution, and then they're fine tuning a language model on it. And then another approach is like Ryan Greenblatt's one, where you use it as an idea generator, just like you advocate.
Exactly. So Ryan Greenblatt's one is actually very much this sort of LLM Modulo version, because they have Python interpreter. So they generate a huge number of code snippets and then check whether or not those snippets could have generated the right results on essentially like the ARC training data. And that kind of gives them a huge advantage. And it's a very reasonable thing to do. But it's basically the guarantee is coming from this interpreter. As we were talking earlier, formal languages have interpreters. Natural languages don't. So by actually converting the whole thing into, I will guess the Python code for solving the ARC challenge, right? You now can depend on the help of the Python interpreter to make sense of whatever you guessed. And you can at least compare the expected output with, what actually output, this particular piece of code is generating. At a level, it is still extremely brute force way because they're generating huge numbers of combinatorial possibilities, and you have to make sure that it is diverse enough. So in general, this is again similar to the LLM Modulo stuff that I talk about, where these are sort of generate test approaches where tester is an external thing which actually can give guarantees. And the soundness is guaranteed by the tester. The completeness depends on the generator. And as impressive as LLMs are, there are no guarantees that they're complete. This is sort of goes back to this issue of, yes, they're creative, but can they create every possible thing? And in general, that almost requires a prompt diversification strategies, where you bring in extra outside knowledge to tell them, okay, now stop generating this kind of code, generate this other kind of code. Because you're then introducing some sort of an inductive bias saying, I believe that, you should also consider this other kind of code because maybe one of them might actually pass the verifier test. That is this extra knowledge that you're bringing in. This old idea, this idea of tree of thoughts that, basically people, that's become very popular, actually is best understood in that way because it's really a prompt diversification strategy which brings in external knowledge to push the LLM.
Yeah, so I interviewed Ryan Greenblatt, and unfortunately he still thinks that, because obviously I asserted that it's, you've got a system 1 and system 2, you've got a neurosymbolic model, it's only working because you have the Python interpreter, verifying. And he was adamant that, no, just wait until the next GPT model comes along, it's going to, but the beautiful segue is that he did a few things, right? He did chain of thought. So, he kind of he carved up the space. He did self-reflection, so refinement of the solutions. And he believes deep in his bones that the LLM can autonomously verify itself and come up with the right solution. Yeah. You've done some very interesting work in this area.
So I completely am on the other camp on this, that for the correctness verification, LLMs just are actually no good. And in our own experiments, where basically, first of all, you have to talk about correctness and verification where there is actually a formal specification of what correctness is. And in those cases, and so I tend to differentiate between tacit versus explicit knowledge tasks. And tacit knowledge tasks, there is no actual formal specification. There's no formal way of saying what makes something a cat or a dog or something else. And the tacit knowledge tasks are the ones that we share with all the animals. We can deal with it. And in fact, those are the ones, they're very messy and there's no formal description. But the civilization that we built, that the animals don't have, very much depended on this addition of the explicit knowledge and verification. So I don't want to get on the plane and hope that it will get somewhere. I want to be able to trust that somebody did the detailed calculations to make sure that there is enough fuel and all these other things, and that it'll actually reach its destination. There's always got, other exogenous events that can happen, but there should not be any egregious, let's just hope that, it might work kind of a thing. So to me, that's what's the kind of verification that we should be interested in. Tacit knowledge tasks are typically about style. Explicit knowledge is about correctness. For the correctness, things like, we basically in our work, we looked at both planning and constraint satisfaction problems, graph coloring kinds of problems, and also looked at the 24 puzzle, which has become somehow popular in the LLM community. All of them have formal verification possibilities, right? You can give a solution, you can give with full guarantee, you can check, whether or not it's a solution. So what we did was we let LLM criticize its own solutions versus it's being criticized by an external verifier. When the LLM criticizes its own solutions, its accuracy goes down, not up, but down. And that's because when it is critiquing its solutions, it hallucinates false errors as well as misses actual errors. You see what I'm saying? And because of which, then it can very easily, if it blundered onto what is actually a correct solution, instead of stopping, it might continue changing it such that it becomes worse. And it's fascinating. And so because of which, when they do self-reflection, quote unquote, they actually worsen. And however, if on the other hand you have an external verifier which is giving an external signal about whether or not it's correct, even as simple as it's not correct, is actually enough to improve the performance. So this is basically the beginnings of what I've been calling LLM Modulo systems, where LLM generates the guess, external verifier gives at least a binary signal saying, this is not right, try once again. And at this point, so the very simplest idea would be they generate like 150 solutions and you check if any one of them is correct. The external verifier, checks. Okay. LLM saying that, okay, one of these must be right is not enough. You need to actually say which of these solutions is actually correct, and that's what the external signal does. And then you can do it more incrementally by saying, okay, here is what is wrong with this solution, here are the errors, and then as a back prompt, and then LLM can potentially use that information in coming up with a new guess. Now, when I say potentially, we don't quite really understand what happens when you give a prompt to LLM and how is it actually, quote unquote, using that prompt to come up with the next completion, other than at the level of conditional probabilities, about the next token, right? So we are in this strange world where LLMs are at once going to, basically, we talk about the fact that they can have million-word context, and at the same time, I can give a 10-word context and they will do the wrong completions. So it's an interesting kind of a shallow use of prompt rather than any deep, I understand the prompt and I'm able to actually use it in generating next tokens. But this back prompting, essentially, at least we do agree that we can see that it'll at least bias it towards a different set of completions. And the hope is a verifier will check those completions and see if they are actually error-free. So that's basically the way verification would work. most of the time when people think LLMs are actually verifying, they tend to confuse style versus correctness, content. So many of these papers have been written on the LLM improved its essay. I would argue that the improved essay is actually a tacit knowledge task. There is no simple formal system which can take an essay and say it is correct, right? Because you're tending to basically look at the kind of a style characteristics rather than, in fact, if you have a beautifully written essay which at some point of time has a fatal factual flaw, they're not going to be able to find it, right? And yet, if in fact, then basically what they'll do in these cases, they will do human subject studies. And you ask humans, are these better essays versus worse essays? And they might find that somehow the essay quality has improved with the LLM critiquing itself. But that's the style improvement, not the correctness improvement. And in fact, in the LLM Modulo architecture, we basically say that you can critique both the style and correctness. For the correctness, it's actually in some sense boring. But, because one of the interesting things is you could have a correct plan that doesn't have the right style. So I give this example of a correct travel plan to come to Vienna from India, where I started, is walk 1 mile, run for another mile, then bike for another mile, etc., etc. By the end of which, indefinite number of these actions, I will be in Vienna. That is sort of correct, but it is highly bad style. Most people would not consider that as a reasonable travel plan because they tend to stick to like an airline flying or some other kind of, standardized versions. So the style is something that LLMs are actually better at critiquing. The correctness is something that they cannot, and you want the external verifiers. And it's a complementary thing because classical AI systems are actually much better at correctness than style.
Yeah, I agree with you. So I'm kind of like a philosophical rationalist. I think we should be reasoning in the domain of certainty. It's either correct or it's not correct. So we agree with that. But devil's advocate for a second, there are folks who think we can do end-to-end predictive models and we can do this active inference and we can just keep leaning into the test instance and fine-tuning and fine-tuning and fine-tuning. And then, we can't verify it. We don't know that it's correct, but we can build systems that work, reasonably robustly and produce often the correct answers. Do you think that that's a reasonable thing?
Yeah, I think the point there is, first of all, the end-to-end correctness. You can use the world itself as a verifier, right? And that is an idea that works only in ergodic domains where, in fact, the agent doesn't die, when it's actually trying its bad idea. So even when you're doing end-to-end verification, there needs to be a signal as to whether the output is actually correct. Where is that signal coming from? This first question. The second question is, how costly is this going to be? Because this is sort of the whole Q star anon conspiracy that I tend to call, because remember for a while back, people were saying there's this Q star algorithm that OpenAI is working on, it will do wonders, etc., etc. And obviously nobody knows whether anything was done, etc. But, some of the ideas that were being floating about were this idea that this sort of a closed, you will have some kind of a verifier with which you kind of generate synthetic data and then you fine tune the system. But there's no universal verifier. Verifiers are problem specific. And fine tuning is a fine enough idea, but ultimately the question about fine tuning would be amortization costs. In general, even for simple fine tuning, right? As I told you, the blocks world, basically these LLMs do badly. So I can always fine tune and basically get them to solve, fine tune with like a gazillion blocks world instances, and it improves performance. Let's say 3 to 4 blocks, it improves performance on 3 to 4 block stacks. But then when I say 5 to 6 block, it will again fall down. And a variation of this is Agent Choice Groups experiments where they did 4x4 multiplication with LLMs. They suck. They then do 4x4 multiplication with fine tuning with like 1 trillion or so pairs of 4x4 digit multiplication and their answers, and they paid an arm and a leg to like Sam Altman, like I think 150,000 or something. And then they got the 4 by 4 multiplication to have 98% accuracy. Let's leave for 1 minute the silliness of why do I want LLMs to do 98% accurate 4 by 4 digit multiplication when I have cheapo calculators that will give you 100% accuracy. But the more damning thing is then they give a 5 by 5 digit multiplication, it goes back to 0. So this is the amortization argument. This is actually the same problem that occurs for chain of thought. Basically, when you give an example, so fine-tuning and chain of thought are very closely connected. So chain of thought essentially gives kind of an advice about how to solve a couple of examples, and you're hoping that LLM learns something from these examples. But as an old AI guy, I know that advice taking is AI complete problem. In fact, John McCarthy, is the founding fathers of the, with Marvin Minsky, Alan Newell, and Herb Simon. He was one of the 4 people, who did this, Dartmouth conference. And John McCarthy said that the holy grail of AI should be an advice taker program. So you give it advice, it will follow that advice. In general, that's an extremely hard thing to do. And in general, you would like to have an advice taker to whom you can give very high level advice and they will follow it, right? In general. And chain of thought makes it look like LLMs can do that. But what they really wind up doing is, if you, for example, tell them how to solve like a 3-4 block stacking problems, they actually improve their performance on the 3-4 block stacking problems. But you increase the number of blocks, the principle remains the same. In particular, for example, one chain of thought idea is, in the blocks world, you can always put all the blocks on the table and then just construct the stacks as you need in the goal state. If I sell this to a kid, they understand this, and then they can do it for 1 block or 15 blocks or 200 blocks until they get bored. But LLMs basically don't get the procedure. They only do better for the 3-4 stacks, and then as you increase the number of blocks, they die. And it turns out it doesn't even need the planning. It actually can be doing, like the last letter concatenation is this much simpler problem where, given a couple of words, dog and cat, you want LLMs to say G and T, because G is the last letter of dog and T is the last letter of cat. And original COT paper basically said, look, off the shelf they can't do it, but if I give this advice about how to do this, they seem to do much better. And we basically did this experiment where we increased the number of words. Having given examples for 2-3 word problems, we increased the number of words. And that should be very reasonable. If you want an AGI, it should at least understand that last letter concatenation is a simple problem where the number of words, you just basically repeat the same thing. It dies. So I keep telling that, this is a sort of the advice taking in general, it sort of reminds me of this old capitalist the proverb that teach a man how to give a man fish and you will feed them for a day, and teach a man how to fish, you will feed him for life. And chain of thought acts as if it's a second, but it's actually a weird version of the second, where you have to tell LLM how to fish 1 fish, how to fish 2 fish, how to fish 3 fish, etc. At which point you will basically lose patience, because it's never learning the actual underlying procedure. It is basically just taking the examples and that of the length that you gave, and it's doing sort of a more or less pattern transfer there as against any sort of procedure learning. And interestingly now, at least I know that Dale Schurmans, who is one of the original authors of the Chain of Thought paper, he gave an invited talk at ICAPS, which is the Automated Planning Conference. He basically said that whatever we are saying is in fact true, that they have the trouble in actually following the procedure. The point was, at that point, original results basically left it to people's imagination that maybe it will learn. I'll give how to do 3 to 4 blocks, and I'll test again on 3 to 4 blocks, and then the performance increased. I didn't say anything about what happens if you increase the number of blocks. And a sign of hype cycle is people assume the best rather than the worst about what happens when you actually increase the if you increase the problem size. And, they didn't claim it will do better, but they kind of left it unsaid and people assumed it is doing it. But then it turns out, once you actually point this out, once you realize that it's not general advice taker at all. So chain of thought it's not what people intuitively believe, because they tend to anthropomorphize and they think, if I tell a person, this is how you solve 3 blocks, the problems, basically put all the blocks on the table, they will be able to solve any number of blocks. And the same thing for last letter concatenation. And they think that's what LLMs are able to do. But no, that's not what they're able to do. They're actually only able to do it for the number of words that you gave the examples. If you increase the number of words, they are not getting the general principle.
So a couple of things. I mean, first of all, many of these techniques, they brittleize the model in the sense that they make them quite domain specific, even if we do external verification, but also things like RAG and tool use and chain of thought. These things kind of make the models quite domain specific. But the bigger problem I wanted to point out is that we want to teach the models how to fish, but the models don't know how to fish in principle because they're not Turing machines. Mm-hmm. You gave the example in your paper here of, like a semi-decidable problem, and maybe you should bring that in, but these aren't solvable in principle in language models.
So actually there is an interesting point there, that many of the bad ideas in LLMs come because of the wrong connections people make between computational complexity and what LLMs do. Okay. In fact, for example, the very reason why people thought LLMs can be better at verification is generation is typically computationally harder than verification. So they just assumed that maybe they can't do the harder problem, they can do the easier problem. The reality is they're not computing the solution in any which way. So in fact, as many people have pointed out, if I consider the following thing. If I have 5 different prompts, let's say, the one prompt basically implicitly, for those of us who understand English, it's implicitly asking for a solution for a constant time computation problem. Another one is linear time. Another one is polynomial time. And then all the way to another one is undecidable problem. And for all of these, the answer is yes or no, let's say. Except if you want to give the guarantee, you need to actually do the computation. Ask yourself, is LLM going to take more time coming up with the token yes or no, depending on the prompt? No, it basically just takes constant time to come up with the answer. And so people try to say, people basically try to say then that since it's anyway going to give it in constant time, let's make it put out more tokens so that altogether it will take more time. First of all, that's somewhat of a silly idea, because there are 2 different ways. One is that really egregiously bad, silly ideas. There's actually a paper, I forget who the others were, who said, let's pause. Let's actually put pause tokens in LLM, hoping that then that way it will start reasoning, because constant time, it can't possibly be reasoning. So you just make it pause and maybe somehow reasoning will occur. That's totally magical thinking. Okay. The other one is you then split the problem into subparts somehow, and you do a whole bunch of work and somehow convert this prompt into multiple other subprompts. And that's the kind of thing that people have been looking at. But you have to remember that in that case, you're doing the computation, not the machine, not LLM. You are doing the computation. And so it still doesn't actually. The computational complexity metaphors are mostly irrelevant for understanding how LLMs are actually, completing the prompts. There is a very different question of, can transformer networks Turing complete? I tend to argue that that's an orthogonal question. You can make it. In fact, remember, there were neural Turing machines beforehand, and you can actually, transformers with external memory can be made Turing complete. But the real question, there are variations that people have talked about, but the real question is, I think that's not actually impacting how LLMs are, generating the next token, essentially. It's not like they're actually doing Turing computation of any kind. They're just basically picking the next token in constant time. They're n-gram models. And so one of the other points you made with respect to Greenblatt's thing, that's actually the thing that, I mean, first of all, I thought Greenblatt's work, I read that blog. Actually, surprisingly enough, I read your tweet about his work because I was following Francois Chollet's ARC thing, and then you wrote this thing that we talked to. No, sorry, not you. One of the other guys, somebody else said this. But so I went back and looked at the Greenblatt's blog. It was, first of all, I think it's good work. It's very nice work. And I think he's a smart kid. I say kid because most people are younger than me. But I do question this issue of later models will do everything. The real question is, if you're saying the later models offer different architecture than autoregressive LLMs, I have no reason to disagree with you. Because the world is wide. I mean, there's just so many different things you can do. And we never said AI cannot do reasoning. AI systems do exist that do reasoning. Like, for example, AlphaGo does reasoning. It's an RL systems do reasoning, planning systems do reasoning, etc. But LLMs are a broad and shallow type of AI systems. They're much better for creativity than for reasoning tasks. And if you just keep increasing the parameters and the size of the system, I have no rational reason to believe that they can do reasoning. They may be able to convert reasoning into retrieval for larger subclass, and that may be practically enough. Like you can fake reasoning as can I ever be, if they're doing reasoning, then I shouldn't be able to come up with any diagonalization arguments of the kind that I was talking about earlier, such as, changing the names of the predicates or looking at other offsets for the Caesar ciphertext, etc. I don't see that going to change just by increasing the size of the models. And so I don't share that optimism, honestly. In fact, somebody from OpenAI who should know a lot more about reasoning in general than most other people was actually, in an open meeting, was basically, they were just trying to claim, all of them were claiming that, the bigger LLMs will solve the problem, etc. And I asked, why do you think so? And this guy says, but you see that AlphaGo does reasoning. And I said, AlphaGo is not an LLM. AlphaGo is an RL system. And nobody ever said RL systems can't do reasoning. We are talking about whether LLMs by themselves can do reasoning. And that there is no reason to believe they can, and that the size increase is going to make any difference. As I said, we actually play this game where whenever there's a new bigger LLM that comes out, we do the same plan bench experiments on them. And as of we haven't yet done the Llama 3.1 that just came yesterday, but pretty much everything basically dies on the obfuscated block solve problem, for example. Yes. And so there's no real reason to believe that I don't share that optimism. Do I share optimism about can we find some other kind of models? Yeah, of course, that's always possible. I'm a big believer in general, the sort of the promise of AI systems. Okay, I think currently, I think Sarah Hooker talked about this idea called hardware lottery.
Yes.
And once you get when you win the hardware lottery, then basically that thing is what you keep. Instead of doing what you wanted to do, you do the things that the current hardware can do, right? That's what you change your thinking. An equivalent is a software lottery, and LLMs have currently won the software lottery, the architecture lottery. And so people are much more, they have figured out lots of engineering principles to some extent, at least in a small subset of people, as to how to train bigger and bigger LLMs more and more efficiently. And so they're more interested in doing more of that. But to some extent, they're just hoping that will somehow solve the quote unquote, the reasoning problem, but there's no reason to believe that. You have to consider other kinds of architectures. And right now, there are people like Jan LeCun who says that he will do this JEPA style architecture that might help, etc. But nobody is really, not even Facebook is actually doing that, because that's the thing about software lotteries, because there is currently all the resources are going into training bigger LLMs. So my way of looking at it is they're going to be here for a while, and they're actually incredibly useful tools. I'll use them in LLM Modulo fashion with this sort of, back prompting from external verifiers and so on. And so that will be a while before, maybe completely different models will come that might have better properties.
Well, that's a really good segue. And by the way, I'm a fan of H. Jepper from LeCun. But so you've got a position paper out called LLMs Can't Plan, but Can Help Planning in the LLM Modulo framework. Now, by the way, I think if you called it alpha reasoning, that it would be more catchy. but in short, though, you've
DeepMind hasn't been giving me any money.
I know, you need their marketing. This is all marketing, man. But yeah, so I've been a big fan of neurosymbolic architectures for years, but the thing is, this is a different type of neurosymbolic architecture. It's bidirectional, so we want to have the system 1 and system 2, and you've got this idea of critics and reformulators and prompt generators and so on, and this is a template architecture for doing really, really good reasoning. Mm-hmm. Can you introduce it, but can you also compare it to things like, alpha geometry and fun search and stuff like that?
So in general, actually, this is a position paper, and I basically was actually talking about unifying a whole bunch of sane ways of combining LLMs with existing other systems to do reasoning tasks with guarantees. Okay. And that is possible with respect to the whole discussion that we had earlier. I tend to think of LLMs as great idea generators. They can generate ideas about everything. So in the context of planning, they can generate plan guesses. They can generate domain model guesses. They can generate potential elaborations of an incompletely specified problem. All of this they can do without any guarantees. Okay. So, but the ability to generate reasonable guesses is nothing to be sneezed at. And so what LLM Modulo tries to do is to leverage this idea generation aspect of LLMs in a sort of a generate test framework, where the testing is done with a bank of critiques, bank of verifiers, and the LLM itself is generating plan guesses, and some of these verifiers might be model-based verifiers. They might need the planning domain model, and then they can then compare a plan with respect to this planning domain model to check whether it is doing what it's supposed to be doing, right? So when they're able to do that, that's sort of almost like having a Python interpreter for the plan sort of a thing. So where is this model coming from? In fact, it turns out that you can also tease out the model from the LLM by asking, okay, what are the potential actions in this domain? What are the potential preconditions and effects, etc.? And then do a second internal LLM modulo where this guess of the domain model is improved with syntax checks, and also as a final check, there's a human in the loop, who would do once per domain. They will say, okay, this is a reasonable domain model. And, in the old AI, basically, this is the knowledge engineering step. Now the knowledge engineering part is kind of made much simpler because LLM generates pretty good domain models. And so there's a NeurIPS paper on that. And so in some sense, so this is a generate test framework where even the testers themselves you can construct the testers themselves with partial help from LLMs. So they can be used for multiple roles, in this overall architecture. And then there's, even when you have like a bank of critiques, the order in which these critiques are called in can simulate essentially hierarchical planning versus normal flat planning. So for example, if you call certain kinds of critiques earlier, like causal chain critiques, then in some sense you're getting a plan that almost works there in that level, and then you are refining it such that it works for other constraints. But ultimately, the plan comes out of this loop only when all the correctness critiques say we are fine. And one of the other interesting things is we also allow style critiques. And for the style critiques, we actually use LLMs because as I said earlier, style critiquing, there is no other approach anyway. There is no formal verifier that can tell you, is this good style? And honestly, that's the reason why we always assumed, in the human civilization, that style is somehow a lot more interesting than content. Anybody can have content. It is the style that's interesting. And LLMs have just shifted the equation. Everybody can have style. because they can call ChatGPT to get the style. The content is going to be a big issue. But the style verification, we'll have the style critics. So we actually have done, there's a paper that's coming out in Com, which basically shows how you can use VLMs to look at behavior trajectories, videos of behavior trajectories, and make useful criticisms about in what ways are those behaviors good versus bad. And that can still be improved. That can be used as a back prompt to improve the next behavior that's synthesized. So we do all of this. And so this is sort of the way to look at LLM Modulo. And you mentioned things like alpha search and fun search. They pretty much sort of become special cases of LLM Modulo. And obviously, LLM Modulo is sort of like an architecture. The specific domain problem that you focused on will be important. So fun search and alpha geometry in particular, they wind up doing alpha geometry does this, math Olympiad problems. We are interested in planning, a lot more planning problems and so on. But in general, I think that those approaches are very much in line with and, to personally kind of at least subsumed by this general vision of letting LLMs do what they're good at, which is guessing, and letting verifiers do what they're good at, which is given a guess going through the thing. And this actually, interestingly enough, harks back to what you were saying way back earlier about deductive. How do you kind of combine creativity and deductive reasoning? And that's basically the creativity of LLMs. Whatever it is, whatever level they have, is being used in conjunction with this, deductive reasoning abilities of the verifiers. And then that way you can actually make guarantees. And in fact, one of the other things is, if you want to get synthetic data to fine tune the LLMs, right now, basically, where is that synthetic data that's guaranteed to be correct coming from? Whereas with this kind of a thing, actually, whatever comes out is guaranteed correct with respect to the critiques that are giving the badge. And so you can then, if you do enough of these, you can actually then fine tune the LLM. That improves the generator density of better guesses, and that will help. The only other thing that I would mention essentially is, as you first of all pointed out, that this is bidirectional interaction, that the guess will be given to the verifier is back prompting, and the back prompting can be done in different varieties. Like you can do binary criticism saying, try again, this is not correct, or you can give, here is something wrong with the current plan, or you can also be constructive, saying, the critique can be constructive, saying, here, why don't you replace this action with this other action? And when they do that, the critique is using some sort of solving abilities underneath. And since I brought up the solving abilities, I want to also mention that I am a fan of using verifiers rather than solvers directly, because verifiers are composable. You can have multiple kinds of constraints. You can have verifiers for each type of constraints, each type of correctness considerations, and say they become composable. Solvers tend to kind of package them together, and if you stick to a specific solver, you are stuck with their expressiveness limitations and so on. This sort of allows like multiple experts, multiple verification experts, and in fact, some of the real world planning, like the kind of things that people in like NASA do in mission planning, etc. In the end, it's like a bunch of humans, subject experts looking at this plan and then saying, yeah, we are fine. And when all the experts are fine, then you try to send a plan out, and it may still fail because, as real world is very extremely complex, and so you can still have the O-ring disaster. But the whole point of planning is to stop errors, failures that you could have foreseen. Right. And that's the whole point, because it reduces the number of failures. And so in that sense, that's basically the LLM Modulo idea. And it sort of combines what we already have from the verification angle with the so one other point I want to make is that when you're talking about verification, one other thing is unit testing is a kind of a verification. So if you have in code, this also LLM Modulo sort of is connected to the way some of the saner methods in using LLMs to automatically generate code are working on. So there, Python interpreter can take a piece of code that LLM generates and check it on unit tests and say, these are the unit test things, and is it giving the correct answer? Now, if it gives the correct answer on the unit, if it doesn't give correct answer for one of the unit tests, for sure it's not good. You're not going to send it out. But even if it gives correct answer, it may still fail because it only means that it's doing well on these unit tests. So that's like a partial verification, and that sort of makes sense. And in basically automatic programming, community right now, people using LLMs wind up using this. And so I would say that's again consistent with LLM modulo architecture.
Yeah. Final question. We're seeing the crashing together of two worlds now. So in the OpenAI camp, for example, they are talking about generalist foundation models, and we are talking about sort of specialized hybrid models with neurosymbolic architectures and so on. People in the middle are talking about building agentic systems. So one way to implement this might be, okay, well, we'll have a foundation model and we'll do RAG and it will call into LLM Modulo. Another way might be we build a multi-agent system. I mean, how do you see this all panning out?
So the way I think about generalist systems, etc., is that you're essentially, as long as you're sticking to LLMs, you are like VLMs versus LLMs or LLMs with additional extra training, etc. This is all to improve the density of quality guesses that the LLM gives out. Irrespective of that, they will still never be able to kind of guarantee that the solution that they're giving actually has any properties. Okay. But it's sort of, you're being constrained to generate better-ish solutions. Like going back to that old Ramanujan thing, he was obviously, there were things that he said that wound up being wrong. But he was one of the guys who seems to have had very good generator for this particular mathematics, right? So that is kind of the hope that people have on the generalized systems, in terms of improving their accuracy, etc. On the agentic systems, first of all, I kind of am like bewildered by the whole agentic hype because people confuse acting versus with planning. Okay, and my comeback to that is, you leave a gun in a house with a toddler, the toddler would act, but they're not planning necessarily. So that's why we shouldn't have guns. In the country I come from, unfortunately, where there are too many people leaving guns with toddlers around, and it's like, and that is acting is not guaranteeing that somehow. Acting is about affordance. Okay, so you can have, they're almost orthogonal. You could have somebody who can come up with a plan, but they actually don't have the affordances. One of the funniest Far Side cartoons by Gary Larson that I remember is these two cows are sitting in the living room and the phone is ringing on the wall, and one cow looks at the cow and says, here we are sitting and there goes the phone ringing, and here we are sitting with lacking opposable thumbs because we can't pick up the phone. So they actually have the plan of how to actually answer the phone, but they can't execute it because they're missing the affordances, they're missing the thing. Conversely, the fact that you can pick up something, or you can press any little button, or you can make function calls, doesn't guarantee that those function calls will actually lead to desirable outcomes. So most people in agentic systems essentially are just somehow thinking that if you can call the functions, everything will be fine. That's only true in highly ergodic worlds where pretty much any sequence will none of the sequences will fail. So it's the only kinds of cases where planning almost is not needed. That's when you can basically get by. But otherwise, agentic systems require, in addition to planning, the ability to call functions. Okay, but you want to upfront prove to yourself at some level that the kinds of functions that you're going to call aren't going to override databases, lead to loss of data that cannot be reverted, etc. Currently, nobody is talking about those issues. In some sense, you have to kind of orchestrate the plan. Humans have to orchestrate the plan and take the blame, and all the other things that's actually happening is function calling. So that, to me, I think is a kind of a people, I mean, obviously would like to have agentic systems, but to the extent since LLMs can't do planning, I don't expect that anything is going to change unless you can have LLM Modulo agentic systems where the plan is kind of guaranteed there, and then you do function calls. That's sort of a possible thing. So that's how I look at this particular, generalist versus agentic systems versus, and then the final thing is about things like LLM Modulo is, as I said, because LLMs won the software lottery, they're going to be here for a while. I don't know what for a while means. I mean, we are in this, incredible time, as you were mentioning earlier. It's a great time to be alive in AI, and it's like you don't know what's going to happen next week, right? But they would be around for a while, for sure. And so it would be making sense to kind of make them do things in a sane way. And that's where this LLM Modulo architectures, that I'm saying, because that sort of AI already exists. RL systems, verifiers, etc. exist already. And so you can put them together with LLMs to actually, give some modicum of guarantees about the kinds of reasoning correctness guarantees and planning correctness guarantees.
Subbarao, it's been an honor and a pleasure. I really hope that you've inspired more young researchers to go into this field. I mean, could just a final few words on that. Where can people find out more about you? But what kind of research should people be doing?
So I actually think the usual advice I give to grad students is you should have broad knowledge, not just the thing that is currently the most popular, because what happened to some extent is many of the grad students actually haven't done anything with logic and reasoning and deductive closure. Some of these words that we're talking about are not even like the things that they understand. They're very bright people, but they're basically focused on a very particular set of skills. And part of it is because, this stuff is working, logic is old school, etc. But the point is you have to differentiate between normative versus operational uses. Logic still remains the normative way of judging reasoning correctness, right? And so you want to know this so that you can be more careful about the claims you are making, so that you can, for example, understand the difference between reasoning and retrieval. You can understand the difference between a database and an n-gram model and a deductive database. And once you have that, humans are incredibly smart, and certainly smart grad students are even smarter than the rest of the humans, and they can do good work. And in general, my sense is, and the other thing I think we were talking beforehand to have skepticism, because I find that in the era of LLMs, AI has become an ersatz natural science. And so it's like, instead of building an artifact to have certain guarantees, you build the artifact and poke it to see what is it able to do. This whole notion of emergent abilities, old engineers would be scared to death. Like, for example, an old civil engineer, finds out that the bridge over Danube, in addition to kind of supporting traffic, on Fridays tends to whistle and on Saturdays flies. They would think that's a failure of bridge building, right? Because you are supposed to build it for specification. And we are in this interesting world where we are actually developing these huge, large models, and you are poking it to see what they're trying to do. And then there are all these emerging abilities and Sparks papers that are coming out. And what is needed in that sort of observational studies is a rigor about don't stop just because you got one positive result. Actually try to see where else it is actually likely to fail. So a classic example is the chain of thought paper, which is hugely influential, hugely popular. Interestingly, in their paper, they have multiple cases where they applied chain of thought. After like 7 or so cases, in about 4 cases, it doesn't do well. Instead of trying to understand why it doesn't do well, they focus the rest of the paper on the 3 cases where it works well. Right. Yeah. And then the rest of the community just basically went with that positive message. But it's important to understand where it doesn't do well too, because that's like a rigor for observational studies. And once you do that, so we are sort of zoologists right now, because we are basically these, incredibly complex organisms that we are training without knowing what they're supposed to be doing. And we're getting surprised that they'll show some spark here and a spark there. But you want to be able to make supportable claims, and you need to be more skeptical about your empirical claims in particular. And that's the kind of advice I would give. And as far as my work itself, I mean, first of all, thanks again for having me on this. And, I've been going around giving tutorials and giving talks, and, all this stuff is available on our websites. And there are lots of people. The LLM Modulo paper actually talks about lots of other related work that if people are interested in that sort of direction, they can also look at that. But, that's what I would say.
Amazing. And the negation is a good example, by the way. And there was the is a,
okay,
not is it. Have you seen that paper where it's like John Cruise is the mother of so-and-so, and then you reverse it and then it doesn't?
Yeah, the reversal curve sorts of things happen too. But in general, the issue in general is in empirical studies. I keep telling this to my students that in empirical studies, just when you think there are results sort of supporting your hypothesis is when you need to be extremely skeptical, because the human tendency is to let's just celebrate this success and write a paper, and that tends to lead to this sort of a situation where you'll wind up writing papers that are having low half-life period, and they actually kind of collectively push the field in somewhat futile directions. Look, I mean, I don't think there is any simple way. I mean, research is done by individuals and they have all sorts of interesting motivations, and I'm completely aware of that. So since you asked me what advice would I give, I would give this advice, knowing fully well that nobody cares about the advice unnecessarily following, and hopefully somebody might actually pay some attention and that might help. But in general, it's a decentralized process, and it's the only good thing about science is it's self-correcting. There was chain of thought paper, there is also our chain of thought doesn't work paper. And ultimately, I mean, I want to end with this thing that I was mentioning somebody else, that I love this story that one time Albert Einstein was asked by this journalist that, did you know that there is this book by like the quote unquote Aryan scientists saying 100 Aryan scientists against relativity. And what do you think about it? And Einstein said, it doesn't matter. If they're right, one is enough. And if they're wrong, 10,000 doesn't make a difference. Right? Ultimately, that's the self-correcting nature of science. And so hopefully, in fact, there's a beautiful paper yesterday in the Position Papers track, which was the first oral in ICML, about embracing negative results. And I understand that people tend to say, just be positive, not negative. But science, you need to understand both the limitations and the capabilities. As much as, people who may have just tuned in the middle might think I'm kind of a LLM Luddite, I think they're actually incredibly useful. It's just you don't want to be delusional about what they can do. You should know what they can and cannot do so that you can use them correctly.
Subbarao, honestly, it's been an absolute honor. It was worth coming to Vienna and losing my luggage just for this interview.
Thank you very much.
Thank you so much. I appreciate it. I appreciate it.
Thank you.
Right.